Students, welcome to section 4-6, inverse matrices and systems of equations. We start off with the identity and inverse matrices. The identity as a matrix is concerned is a 2 by 2 or 3 by 3, 4 by 4, and so on sized matrix, as is an inverse matrix. But the identity is actually something that we typically don't see in a problem. And in the example below, you're not actually going to see the identity unfold. So what I'm going to do is use the identity in a kind of a verification process manner, while the inverse of a matrix will be something you see quite regularly. The identity matrix for matrix multiplication is a square matrix with ones for every element of the main diagonal and zeros elsewhere. So that speaks to the identity matrix pretty much to a T. And it could be any square matrix. It doesn't have to be a 2 by 2, 3 by 3, 4 by 4. It could be any n by n matrix, as it suggests here, identity matrix for multiplication. If A is an n by n matrix and I is the identity matrix, then A, any square matrix, times its identity is equal to A. And the same holds true if you take the identity I times matrix A, and you get, well, just A in return. It's kind of like multiplying a number by one in a sense. You'll also always get the matrix back. Also, as we saw with, any number multiplied by one. All right, if an n by n matrix A has an inverse, A inverse with this little exponent -1, then A times A inverse, but also A inverse times A is equal to I. This is one of the few times where you can commute matrices and get the same exact answer as a result. And by commute, I mean flip A and A inverse to get really, again, the same result. We talked earlier in a prior section about the idea that matrices, as far as multiplication is concerned, matrices cannot be commuted. Otherwise, you either can't multiply them or you get an incorrect answer or different answer technically, if in fact one exists. But please keep in mind, when multiplying an inverse times the original matrix, you can flip-flop or commute to get the identity. Example, determine whether x, which is a 2 by 2, and y, which is a 2 by 2, are inverses of each other. So here's how this is going to work. If you multiply matrix x times matrix y, just as we learned in the past with multiplication, a 2 by 2 times a 2 by 2 will be in fact a 2 by 2 because the inner values are the same. And the answer will be the outer values. So I take 7, 4, and 3, -5. So I do 7 times 3 plus 4 times -5, 21 minus 20. That's nice. That's 1. I take 7, 4, and -2, 7 halves. 7 times -2 plus 4 times 7 halves, which ends up being -14 plus 14, or 0. And then we jump down to the second row, 10, 6, and 3, -5. 10 times 3 plus 6 times -5, 30 minus 30, which of course is 0. And then 10, 6, -2, 7 halves. 10 times -2 plus 6 times 7 halves, -20 plus 21, of course, which is 1. That is the identity. And in this first example, I had alluded to earlier us not really seeing the identity a whole lot. We are in the process of verifying. So we're kind of warming ourselves up to what the identity is and what it takes to get there. And yes, we do in fact see the identity in the final answer. So although I somewhat misspoke on that, from pretty much this page on, you probably won't see the identity pop up a whole lot. So this is a verification of sorts. So here's your 2 by 2 identity matrix. Ones on the main diagonal, zeros everywhere else. If this was a 3 by 3, you'd have 3 ones and then zeros everywhere else. Okay, let's commute the multiplication here such that it's y times. And again, earlier we discussed that multiplication of matrices is not commutative, but I'm going to try that here and see what happens. 2 by 2 times a 2 by 2, which is of course possible. You can do that because the inner numbers are the same and the outer numbers are your answer. The answer will be a 2 by 2. So 3, -2, 7, 10. 3 times 7 plus -2 times 10, that's 21 minus 20. 3, -2, 4, 6. 3 times 4 plus -2 times 6, that's 12 minus 12. bounce down to negative 5 7/2 and 7 10ths. So negative 5 times 7 plus 7/2, negative 35, 35. Negative 5 7/2, 4 6. Negative 5 times 4 plus 7/2 times 6. That's negative 20 plus 21. All those numbers end up, as you can tell here, as such 1 0 0 1, which again is the identity. Because x times y and y times x both equal this identity matrix, we know that they're inverses of each other. Now, I wanted to take an example, maybe this example, and reflect upon how the OneNote matrix tools would nicely be utilized here. Let's go ahead and do that. We've done this in the past. Do a little copy and paste here. We're going to prove on the calculator, well, particularly the OneNote calculator. Maybe we'll even use the graphing calculator in a moment too. We're going to go ahead and utilize the tools. I was playing with the matrix earlier, so let's delete that. All right, so here we go. So I'm going to insert equation. And I've been using this lately, so let's use that again. Might have to enlarge, so let's go ahead and enlarge. If we use all the tools at our disposal smartly here, and maybe not just what we can see in the problem, but maybe in terms of the efficiency of what also could work here in context. So I could theoretically type in not just matrix X, but I could type in matrix Y. I can multiply X times Y, and I can multiply Y times X. I'm going to do this a little bit differently in this particular case. However, I'm going to take, after highlighting matrix X, and I'm going to go to my math feature, and I'm just going to hit select the action of invert. The invert matrix or inverse matrix option, quick and easy as you can see, and not surprisingly, I would argue, there's your matrix Y. So the inverse of X is Y, and vice versa. If I were to ask you to find the inverse of Y, you would actually get X in return. So instead of multiplying X times Y and Y times X to get the identity, which I could do, just finding the inverse of this should yield that. Pretty nice and easy to see, I would argue. 3, negative 2, negative 5, 7 halves. All right, let's move on to the next page. And we'll continue on maybe applying these ideas in context, because that's really our major goal today, to see how this applies. Matrix equations. A matrix equation for a system of equations consists of product, coefficient, and variable matrices on the left and the constant matrix on the right of the equal sign. Now, in a prior section, we had looked at the Cramer's rule application to solve systems. This is the better of the two choices. For example, use a matrix equation to solve a system of equations. Here's your system of equations, pretty typical looking setup. The coefficients, the variables, and the constant matrices are going to look like the following. So 3, negative 7, 1, 5. On its own, that's going to be a 2 by 2 matrix. The variables in the problem that we're solving for are X and Y. So we write that as a 2 by 1 matrix. Can you multiply a 2 by 2 times a 2 by 1? Well, of course. A 2 by 2 times a 2 by 1, because the inner dimensions are both 2, the resulting matrix, the outer numbers, of course, would be a 2 by 1. Now, it just so happens we know what the 2 by 1 will already equal. It's going to be equal to 12, negative 8. So here's your setup. So we've got matrix, we can call it A times matrix X, and that's going to be equal to matrix B. So what we're going to do is we're going to find the inverse of the coefficient matrix. Now the math that you see here, this is the non-calculator approach to finding the matrix. I'm going to find the matrix using the calculator. I'm going to use the virtual TI-83 here, okay, in context. So let's do that. So we'll go ahead and find the inverse, second matrix. And actually notice there is the X inverse button itself that you could apply most certainly if and when we are asked to. As a matter of fact, let's edit matrix A. as a 2 by 2. And let's type in our values of 3, -7, 1, and then 5. Now, simply those values, again, represent matrix A on the left side of our matrix equation here, right here, the coefficient matrix. Second quit, I always quit, and then I go back into the matrix. Quit every time I'm going to edit and use a math tool. So edit option number 2, and we're going to type in a 2 by 1 matrix here, and that will end up being the right side of the equation. The variable matrix XY is not something we can type in because obviously it's known. So go ahead and type in your matrix B. We'll use that here in a moment. What I do want to do though is go back into the matrix, and I want to hit option 1 and just let the calculator find the inverse. So the inverse again is right here, X inverse. Let the calculator do its thing. What you see here, I will not expect you guys to do, and then in turn find here that 2 by 2 matrix. Let the calculator do it for you. Now that doesn't look like the answer, but if you hit math, option number 1, and hit enter, and there you go. 5 20-seconds, 7 20-seconds, -1/22, and 3 20-seconds. So that in fact is the 2 by 2 inverse. Okay, as we discussed, multiplying an inverse times itself, excuse me, an inverse times the original matrix, or vice versa, will yield the identity. In this particular case, noting the order, however, that we're going to be technically multiplying, I have A inverse times B as the appropriate order. If you flip the order, it's not going to work. I'll show you that in a moment. So we'll do matrix A inverse times matrix B, and this should certainly yield your answer. Now that technically doesn't look exactly like what we see at the bottom, 2/11, -18/11, but if we hit option math, option 1 under math, hit enter, there you have it. So the ordered pair answer to this problem is 2/11, -18/11. Every single system of equations that you ever do, this is probably the best way to do it if the answers are as complicated as this. If you can look at it and do substitution or elimination, one or the other or both easily, I would stick with that. But in the world of matrices, and when you get a more complicated answer, for sure, this is the best approach. It's better than Cramer's rule, in my opinion. Just to prove my last point here, in that the order does matter as far as when you multiply matrices. Let's flip the order. So let's say multiplying matrix B times A inverse. If we try that, it's, watch, going to be, well, think about this. It's a 2 by 1 times a 2 by 2. All right, here was the inverse matrix, 2 by 2. So 2 by 1 times a 2 by 2. Hit enter. Should be an error in the mismatch. There it is, dimension mismatch. The reason that's an error in the dimension mismatch again is because 2 by 2 times 2 by 1 is not possible. The inner dimensions are not the same, so you can't even multiply. Now, you may wonder, well, if A inverse B works, and obviously I just proved that B A inverse doesn't work, why did I flip the order on the prior page? Well, the prior page, when I took A inverse times A, and then again A times A inverse, I was trying to prove that the identity matrix, in fact, existed. But I, again, could only do that because your dimensions matched appropriately. In this case, it's not going to happen that way. I'm not verifying the identity, nor did you even see the identity pop up in the problem. It does turn out, though, when you multiply both sides of the original matrix equation, you don't see the identity, but the identity is, in fact, there in front of X. Not a big deal, but if you do test this theory, I times X would be what you would write to specifically designate how X even can stand alone. So I, again, the identity times X, or remember just simply X as it basically comes out. So that concludes today's notes. Please use your calculator as much as possible as a finishing touch here.